Welcome back, student. We'll start with the next topic today, that is infrared spectroscopy. The learning outcomes. The learner will be able to explain the fundamental modes of vibration in polyatomic molecule, relate factor affecting vibrations and IR spectra, discuss the sample handling technique, and describe instrumentation and application of IR spectroscopy. Up till now, we have studied the various spectroscopy, that is UV spectroscopy, visible spectroscopy, that is absorption spectroscopy. Then we have studied fluorescence spectroscopy, that is your emission spectroscopy. So we are starting with the IR spectroscopy, that is also an absorption spectroscopy. So infrared spectroscopy is the analysis of infrared light interacting with the molecule. So all of you know the electromagnetic spectrum starting from cosmic rays and ending with the TV rays, radar waves. So we know that they are in the continuum. So we know first is cosmic rays, gamma rays, X rays, then vacuum UV, visible, and then comes the IR. So as you are going on to this side, the energy content of the radiation is decreasing and the wavelength is increasing. The main use of this IR spectroscopy is in organic and inorganic chemistry. So basically it is used for detecting the functional group in the molecule for the structural elucidation purpose and for the determination of purities. So all pharmacopoeial methods provides the information regarding purity of the compound raw material, and that can be identified by using the IR spectroscopy. So in IR, the sample is irradiated with broad band of infrared frequencies, and the intensity of reflected or transmitted infrared radiation is measured as a function of frequency. From the knowledge of incident intensity and reflected or transmitted intensity as a function of infrared frequency, an infrared absorption spectrum can be recorded. We are measuring the infrared absorption spectrum. Absorption of a specific frequency is characteristic of certain bonds. So if you see the IR spectrum, okay, the IR spectrum identifies various bonds and the functional group within the molecule. If you see the IR spectrum, so it is a plot of the wave number, that is centimeter inverse versus the percentage transmission. So you have just remember the UV plot. It is a wavelength versus the absorbance. Okay, so we are getting a peak of the material. So the peak is known as the lambda max. We are measuring the lambda max in case of UV. So lambda max is a wavelength at which maximum absorption is observed. Okay, and that is against the wavelength on x-axis and absorbance on y-axis. But here we are having either wavelength or frequency on x-axis and percentage transmission on the y-axis. So instead of getting the peak, we are getting the inverted peaks. So many number of peaks we will get depending upon various functional group within the molecule. So this number of peak is also defined. How many peaks we will get, that depends upon how many functional groups or types of atoms are there in your molecule. So you will get the number of peaks. So this will be the inverted peaks. So this will be the discrete peak, and appearance of peak in the particular regions reveals the information of your structure of the molecule. So that we are going to study. So one more thing that is important, that the physical state of the matter is to be recorded on the IR spectrum, because we can take the IR spectrum in any form, that we can take it in the solid form, in the liquid form, or in the gaseous form. So we must mention the physical state of your matter, that is sample, and the sample is to be dissolved. If it is dissolved into the particular solvent, there may be the chances that the solvent peak will be appearing. So you may see a break in the spectrum, and that is due to the solvent. Okay, so this is to be we had selecting the solvent in such a way that they will not interfere in your determination. So this is the IR spectrum. We can compare the IR spectrum with UV spectrum. So regions of infrared spectrum. So we know that it starts after the visible radiation. So we can see that IR is divided in three main parts, that is near infrared region, mid infrared region, and far infrared region. The usual unit of the IR is in the micrometer. So we can say 0.75 micrometer to 2.5 micrometer. that is near infrared, 2.5 to 50 micrometer, that is mid infrared, and far infrared is from 50 to 1000 micrometer. We can see this unit in meters to just learn the continuation of your spectra. Then frequency is also there, 4 into 10 raised to 14 to 1.2 into 10 raised to 14. So generally we are using either in micrometer, or we are using the wave number as a unit of measurement. So wave number is generally from 13,000 to 4,000 centimeter inverse, number of waves per centimeter, therefore it is a centimeter inverse. So 13,000 to 4,000 is your near infrared region, 4,000 to 200 is your mid infrared region, and 200 to 10 centimeter inverse is your far infrared region. So most of the band that indicates what functional group is present are found in the region between 400 to 1300 centimeter inverse. Okay, 4000 to 1300 centimeter inverse. This band can be identified and used to determine the functional group of unknown compound. So the useful region for our IR spectroscopy is only the mid infrared region. We are not using near infrared region, we are not using far infrared region, but some part of the mid infrared region we are using for the structural elucidation purpose. The bands that are unique to each molecule, similar to the fingerprints, are found in the fingerprint region. So this mid-infrared region is further divided in two parts. One is known as a fingerprint region, and is another is known as a group frequency region, or that is also called as a functional group region. Okay, so functional group region is from 4,000 to 1,300 centimeter inverse, and fingerprint region is from 1300 centimeter to 400 centimeter inverse. So why it is called as a fingerprint? Because it is a unique identifying characteristic for a particular functional group. Appearance of the peak within this region is unique identifying characteristic. But this region, whenever we are observing any spectrum, see this spectrum, when we are observing the spectrum is from 500 to 400. Generally, we start recording the spectrum from 1500 to 3000. Just we'll take this nearer to 3000. So this part means that we are working in the functional group region for detection of the various functional group. Okay, fingerprint region is a complex region, but that is having the unique identifying characteristic. Therefore, it is called as a functional group region. So you just have to remember these two part, that is your fingerprint region, that is from 1300 centimeter inverse to 4400 centimeter inverse, and functional group region, that is 400 centimeter inverse to 1300 centimeter inverse. Okay, so this is all the regions of the infrared spectrum. So what happened after the absorption of infrared light? There are three main processes by which molecule can absorb the radiation, and each of these routes involves an increase in energy that is proportional to the light absorbed. So resonance, in every spectroscopy we have seen that resonance is taking place, means they absorb the radiations, they goes into the excited state, they will not remain long time in excited state, they will try to come back to the ground state by remitting back the energies either in terms of the radiation or in terms of the heat. The first route involves the electrons of molecules being raised to a higher energy level, which is there in the electronic transaction. So all of you have studied the electronic transactions in UV spectroscopy. In case of UV spectroscopy, there is energy content is sufficient to produce the electronic transaction. Do you remember how many electronic transactions we have studied? Okay, just pause this video and recall what you have studied in the previous lecture. Write down on your notebook that how many transactions we have studied and what was the energy content of those transactions. If you have finished, play the video and see that there are only four transactions we have studied. The highest energy requiring transaction is from sigma to sigma strike. The next energy transaction is from N to sigma strike. These two transactions are possible in vacuum UV. So they are not also studied. Only two types of the transactions we had to learn, that is from pi to pi strike transaction and N to pi strike transaction. So these are related to the energy content of the radiations. Okay, so electronic transactions are possible in UV. So in case of your visible, in case of your infrared radiations, two types of transactions are there. Either there will be the rotational transactions or vibrational transaction. So we are not studying the rotational transactions in case of with IR radiations. Okay, we are studying only the vibrational transaction. Rotational transactions are in the electron spin resonance spectroscopy. The second route occurs when absorption of radiation leads to the higher rotational energy level in rotational transaction. The third route is vibrational transactions, which occurs on absorption of quantized energy. This leads to the increased vibrational energy levels. It is important to state that energy is quantized and absorption of radiation causes molecules to move to the higher internal energy levels. Okay, so there will be after absorption of energies, the molecule will go from the lower vibrational energy level to the higher vibrational energy level. So we can characterize or we can categorize these transactions as electronic transaction, vibrational transaction, and rotational transaction. Rotational transactions are again requiring less energy as compared to vibrational transactions. So when we are thinking of the UV radiation, the more important transactions is electronic transactions. No doubt, the vibrational and rotational transactions are happening, but we are only studying the electronic transaction in this case. In case of IR, vibrational and rotational transactions are occurring, but we are only studying the vibrational transaction in case of IR. And in case of electron spin resonance spectroscopy, only the rotational transactions are occurring, and that we are studying. So what is the basic principle of infrared spectroscopy? The energy of infrared radiation is weaker than that of the visible and ultraviolet radiation, and so the type of interaction with matter is different. Absorption of IR radiation leads to the vibrational transactions. Okay, the atoms within the molecules are attached with certain bonds, and when we bombarded these radiation energies, these bonds will be getting vibrated, and that we are measuring in case of IR. A certain requirement of IR absorption is net change in dipole moment in molecule as it must vibrate or rotate. Just pause this video and recall in case of your UV, what is the minimum requirement of UV absorption? Okay, just note down in your notebook what is the minimum requirement. Okay, if you are finished, then I will just recall you the minimum requirement for UV absorption, that there should be the pi bond system and there should be non-bonded electrons. Then and then only this pi to pi stack transaction and n to pi stack transaction are possible in case of your UV spectroscopy. Here, what is the basic requirement? That there should be the change in dipole. What you mean by dipole? Means whatever groups present in your, there should be the different groups attached to a certain atom. Okay, if you are taking carbon, it should be attached with a different group, so that there should be a change in dipole, there should be change in charges, and that is minimum requirement. And the vibrational frequency should match with the frequency of the vibration of atom, then and then only this absorption of IR radiation will take place. So two things are there, that there should be a change in dipole, and the vibrational frequency of your atom should match with the vibrations of your bonds. As a molecule vibrate, there is a fluctuation in the dipole moment. This causes field that increase with the electric field associated with the radiation. If there is a match in frequency of radiation and the natural vibration of the molecule, absorption occur, and this alters the amplitude of molecular vibration. Means when it is in the lower vibrational conditions, it will absorb these radiations and it will goes into the higher vibrational level. Okay, so that is called as a fundamental vibrations and overtone vibrations. These are the terminologies. We'll see the terminology later on. Fundamental vibrations and overtone vibrations. Molecules such as oxygen, nitrogen, bromine do not have change in dipole moment because they are diatomic molecules and having the same structure. There is no change in the component, so they will not produce any vibrations. They will not produce absorption of the IR radiation because there is no change in dipole. amplitude not orientation. When they undergoes the rotational and vibrational motion, as result they cannot absorb the IR radiation. These are the non-absorbing because they are the diatomic molecules of similar nature. Okay, they will not have the different group attached, so there will not be any change in the dipole moment, and they will not show you the IR absorption. So for IR absorption there should be the different groups attached into the carbon, therefore it is used to detect the functional group. How it can detect the functional group? Because the main thing is that there should be the change in vibration, there should be change in the charges on the molecule. Okay, so diatomic molecular vibrations are generally studied by using the Hooke's law of the simple harmonic motion. The absorption of IR radiation by molecule can be linked to two atoms attached to each other by a massless spring. We will consider these bonds as a massless spring. Considering simple diatomic molecule, only one vibration is possible. Okay, so when we are having the diatomic molecule, means if there is a carbon attached to one hydrogen, so what will happen? So when we give the torque to this hydrogen, so they will get vibrating, means there is change into the bond length. Okay, so we can see there are two types of the vibrations occurring. Either there is increase in the bond length or decrease in the bond length, or there is change in the angle of your bonds which is attached to the central atom. The Hooke's law potential, on other hand, is based on ideal springs. Solving the Schrödinger equations for harmonic oscillation potential results in energy level results. Okay, just for your understanding purpose, I have just collected one animations. I will show you this animation that you will understand. So this is okay. Just I will again explain you this spring structure. You can see this. Okay, so we are what we are considering, we are these are the two atoms which are attached with the bond. So we'll consider this spring as a bond, and we are just measuring the strength of this spring. Okay, the vibration depends upon the strength of spring. If this spring is hard or it has a more strength, uh, see like this will vibrate more, and if the atoms are bulky they will vibrate slowly. Means the vibration depends upon two things, that is your either the strength of spring and the differences between these two atoms. The harder spring vibrate faster than this normal one. Okay, so this is the things what we can observe. Now we consider this is the normal vibration going on. So now we if we bombarded the energy of the IR radiation, it will absorb this energy and it will start vibrating in the higher level. Okay, so this is what we have to learn in the IR spectroscopy. Now we have studied this simple harmonic motion of your according to Hooke's law. So this Hooke's law, restoring the force of a spring is proportional to the displacement. Okay, so what is the displacement? That is F equals to minus Ky, where F is a force constant and K is a force constant. F is a force and K is a force constant. Okay, stiffness of spring. What is the strength of spring? And y is a displacement. Okay, so how the molecule will get displaced? Okay, so this is the hyperbolic graph to show you the displacement. Okay, so this either there is a plus displacement or minus displacement. You just recall your pendulum experiment what we are doing. So when we are giving a jerk to the pendulum and we are measuring the distance how much it will get displaced from the central point. Okay, that is minus x. So that we are determining either plus x or minus x, how much distance it will get displaced. And same thing is there in the case of IR also. So we are measuring this displacement, how much plus a or plus x, we can say plus x or minus x displacement is there from the central point that we are measuring, and that is according to Hooke's law. So natural oscillation frequency of mechanical oscillation depends on masses of object, what we have studied, and force constant of the spring, that is the bond. Okay, what is the strength of the bond? Oscillation frequency is independent of the amount of energy imparted to the spring. So how much energy we are supplying, that depends upon that. We are not considering, we are considering only the differences between these two atoms and the strength of spring. And just by doing this Hooke's law calculations, we can calculate the frequency at which the molecule or the functional group will appear in the IR spectrum. So we can have two types of the things, that we can have a diatomic molecular vibrations, that is we are seeing here. So diatomic molecular vibrations and polyatomic molecular vibration. Polyatomic means more than two groups are attached, then that is called as a polyatomic molecules. Vibration motions are defined by stretching and bending modes. So there are two types of the vibrations occurring. In large molecule, several vibrational motions are observed when there is a continuous change in interatomic distance along the axis of bond between two atoms. This is known as stretching vibration. Okay, stretching vibrations is related to the change in bond length. Okay, so when there is a increase in bond length or decrease in bond length, that can be studied by using your stretching vibrations. Okay, a change in the angle occurring between two bonds is known as a bending vibration. Okay, so there are two types of vibration: stretching vibrations and bending vibration. Bending vibrations are related to the change in bond angle, and stretching vibrations are related to change in the bond length. Four bending vibrations are exist, namely wagging, twisting, rocking, and scissoring. Okay, so if you take any diatomic molecule or polyatomic molecule, in diatomic molecule there are two types of the stretching vibration, and in polyatomic molecule there are four types of the bending vibration. So you consider CH2 group is used as examples to illustrate the stretching and bending vibrations. You can see here. So stretching vibrations, so these are called as the stretching vibrations. Stretching vibrations are rhythmic movement along the bond axis with a subsequent increase and decrease in the bond length. So they are related to the bond length. So you consider this as a carbon which is attached to two hydrogens. Okay, so either this bond length increases or this bond length decreases. Okay, so both of them at a time, if increase or decrease, that is called as symmetric vibrations. And in asymmetric vibration, when bond length of one is increasing, the another is decreasing. So these are the asymmetric one. So there are two types of the stretching vibration, either increase in bond length or decrease in bond length. Okay, so these are related to the bond length. Now your bending vibrations are also of two types. Okay, so we can see these bending vibrations. Bending vibrations are either in plane bending vibration or out of plane bending vibration. So these two are the in plane bending vibration, and these two are the out of plane bending vibration. Out of plane means they are 3D vibrational modes, and these are the 2D vibrational modes. So in plane bending vibrations are again of two types: in plane rocking vibration and in plane scissoring vibration. Okay, so these are in plane vibrations. So rocking means they are moving either to this side or to this side. So they are just rocking around your carbon. So this angle is changing. Okay, so there is change in angle at this side. So they are in the same plane. Therefore, they are called as an in plane rocking vibration. In case of the scissoring vibration, so they are coming either together or they are just going outside. Okay, so this angle we are observing in case of the in plane. So here there is stretching change in bond length, and here it is change in your bond angle. So these are all two in the in plane. Now out of plane means there is a involvement of x-axis. Okay, either we can see in many book it is written as a far, near, or plus minus. Okay, so if it is coming in three-dimensional z axis, okay, either it is coming far or near to each other. So therefore it is out of plane band vibration, that is called as a wagging, or out of plane twisting Okay, so they are twisting around this axis. So there is again change in the bond axis. So that we are measuring. So these are four types of the bending vibration, and these are two types of the stretching vibrations. A change in bond angle or movement of group of atoms with respect to the rest of molecule. Okay, so rocking, scissoring, wagging, and twisting. These are four types of the bending vibration. Now, degree of freedom. One another things what we have to study in the theory, that is degree of freedom. How many moments are possible within the molecule? Okay, so how many moments are possible? So that is known as the degree of freedom. A molecule consisting of n number of atoms has total 3n degree of freedom corresponding to the certain coordinates of each atom in the molecule. So there are three axes: x-axis, y-axis, and z-axis. If there are the n number, so this all atoms will move on these three axes. So therefore, it is called as 3n degree of freedom. Okay, so this 3n degree of freedom depends upon linear and non-linear molecule. In a non-linear molecule, three of these degree of freedoms are rotational and three are transitional, and the remainder is the fundamental vibrations. Okay, in linear molecule, three are transitional degree of freedom and two are the rotational. So this formula varies for the linear and non-linear molecule. This is because in linear molecule, all of the atom lies on the single straight line, and hence rotations about the bond axis is not possible. Mathematically, the normal mode for linear and non-linear can be expressed as linear molecule will has 3n minus 5 degree of freedom, and non-linear molecule will has 3n minus 6 degree of freedom. Now, all of you are thinking why I am giving you all this degree of freedoms and everything. Okay, so what I am saying, see here, 3n minus 5. 3, n is the number of atoms, minus 5 is the value. Okay, so if you say CO2, carbon dioxide, okay, 2 oxygen and 1 means 3. Okay, 3 into 3, 9, minus 5 means 4. Okay, so it will give you the 4 answer. And what is 4 means? Means it will produce 4 peaks into the spectrum. That is related to the degree of freedom. Means if you know calculate degree of freedom, you will calculate how many peak will appear in the IR spectrum. Okay, so for linear molecule and non-linear molecule, 3n minus 6 is for the non-linear molecule. Okay, so non-linear molecule, so consider benzene. Okay, benzene, how many peaks will be there? How many atoms are there in benzene? C6H6 means 6 hydrogen and 6 carbon, 12. 12 threes are 36 minus 6 means there will be 30. Means if you see the IR spectrum of benzene, you will get the 30 peaks in the spectrum. Means this degree of freedom will be useful to know how many peaks will appear in your IR spectrum. I will illustrate this you in the next slides. Vibration of water. Okay, so water molecule is non-linear molecule due to the uneven distribution of electron density. So this is linear or non-linear. So you should know what are the linear molecules and what are the non-linear molecules. So if you see the water, the total degree of freedom for water will be 3 into 3 minus 6. Okay, 3 into 3 minus means 6. 9 minus 6 equals to 3 degree of freedom, which corresponds to the following stretching and bending vibration. The vibrational modes are illustrated below. Okay, so if you see this, these are the symmetric stretching vibrations, symmetric stretch and scissoring or bending. This is the bending vibration. So three vibrations will be there. Either there will be asymmetric stretch or symmetric stretch, and there will be the bending. Okay, so these three vibrations will be there. If you see the IR spectrum of your water molecule, you will get the three bands in the IR spectra of water. Now, for example, you go for the carbon dioxide, it is the non-linear molecule. It is a linear molecule. So CO2 is a linear molecule. So we had to use the 3n minus 5 as the formula. Okay, it has four modes of vibration. So 3 minus 3 into 3, that is 9, minus 5. So it will be 4. So carbon dioxide has two stretching modes of the symmetric and asymmetric, and two bending modes. Okay, so see here. So these are the symmetric stretching and asymmetric stretching modes of your carbon dioxide, and these are the bending vibrations of your carbon dioxides. Carbon dioxide has total of the four stretching and bending modes, but only two are seen. The two of its bonds are degenerate, and one of the vibration modes is symmetric, hence it does not causes a dipole moment change. Okay, therefore many times we can see no peaks in case of the carbon dioxide. Okay, so I think this is sufficient to for this lecture. You will see you in the next lecture for the rest of the topic. Thank you.